the 59th episode of PEEPanEIP, an educational video series where we learn about an Ethereum improvement proposal, upcoming upgrades, and the basics of Ethereum block. I'm your host, Pooja Ranjan, and today we are going to talk about EIP-3668 CCIP Read Secure of Data Chain Retrieval with our special guest, Nick Johnson. And we are also joined by William Schwab, Alita Moore, Brent Alsop, and Shubhangi Gokhale from the Ethereum Cat Holders team. As most of you already know, Nick Johnson is the lead developer of ENS, former EIP editor, and of course, the lead author for the EIP-3668. He was on the show in the past to talk about potential direction for new EIPs, a couple of other proposals, EIP-137, that is Ethereum Domain Name Service, and the EIP-2544, which is ENS Wildcard Resolution. So if you missed it earlier, please check out the episodes 17 and 29 on the PEEPanEIP playlist. Video links are also be found on the top right corner of your screen. So back to today's proposal. EIP-3668 is a standard track EIP of ERC category. To learn more about the proposal, let's welcome Nick Johnson. Thank you for joining us, Nick.
Hi, thank you. Pleasure to be here.
It's always a pleasure to have you on this show. I understand this is a relatively new proposal and you have a lot to unpack. So without further ado, let's peep in.
Sounds good. So, as you already know, I'm Nick Johnson. Today I'm here to talk about our off-chain secure data retrieval, but all of this happens through the aegis of my work on ENS. So today I'm going to go over what the problem that we encountered is that motivated us to build this in the first place, a sort of a review of the existing ecosystem tools, why we couldn't identify anything that already did what we needed to do, the proposed architecture for 3668, a very short demo of how it works in practice, and then some more information on what we've done so far and what our next steps are. So first of all, it's really useful to start by talking about what it is that we're actually trying to do and why we found the need for a standard in the first place. So with ENS, one of our primary goals at the moment is to move as much stuff to L2s and off L1 as possible in order to optimize gas efficiency and reduce costs for users. And in doing that, we have some fairly unique requirements that are different from your average, DeFi or token application, in that most of ENS is concerned with read activity, with people resolving names and so forth. And so we have some fairly unique requirements. We don't want the clients, that is the pieces of software that do the resolution, like your wallet, to have to know how to query every different L2. And we want the owners of names to be able to choose the L2 of their choice rather than having one forced on them as, now ENS is on Polygon or any other network. And when clients are querying an L2, we need no additional trust assumptions. So if it's a true L2 that has no trust assumptions for verifying state, we shouldn't be introducing any with like a consortium of signers or anything like that. Without any L1 commits on update. So that means that if you own a name and you've moved it to say Optimism and you want to create a subdomain, you shouldn't have to create a transaction on L1 and nor should some backend system have to do so. And without any transactions for queries, obviously, because when you look up a name in your wallet, it would be intractable if you had to do a transaction in order to make a query. And without any hard requirements on the capabilities of that L2. So we want to support not just EVM compatible L2s, but a variety of other L2s. And as you'll see soon, even things that aren't strictly speaking L2s at all. And this seems like a fairly steep list of requirements, nigh unachievable perhaps, but it turns out that a solution is both practical and really fairly straightforward. So our first step was to look at how existing L2 integrations work. And so the interaction model on existing L2 integrations tends to be quite different from what we need. The basic high-level primitive that's typically provided is token bridge. So you have a token on L1, you want to move it to, say, optimism, you use some sort of bridge, and what that does is it locks up your token on L1, and it creates a clone of that token on optimism that you can then use and move around and so on. And if you ever want to move it back, then it burns that token on optimism and it unlocks it on L1 to whoever the new owner is. And this isn't really something that's very useful for ENS or other applications that are focused on read activity. There's no obvious way to turn this into a way to move ENS names off chain and do secure resolution. But token bridges are typically built on top of another primitive, which is message passing, a way to send a message from L2 to L1 or L1 to L2 and have the recipient be sure that it was legitimately authored by the counterparty that claims it was. And this is closer to what we need because it provides us with a way to just send messages rather than tokens. But it still doesn't really satisfy our requirements because we are in a situation where, we would have to send transactions to L1 in order to update a name on L2, or in a situation where you need to send a transaction in order to resolve a name. And we've already said neither of those are acceptable. So what's message passing built on? The basic primitive for pretty much all bridges is prove something exists or happened on L2 or vice versa for L1. And this is a much more useful primitive. So to give you an idea of how this works, when you send a token from Ethereum to Optimism, what it looks like is that you're sending a token. Underlying that, you're actually passing a message from Ethereum to Optimism saying, I locked this token, please give, mint one for me on Optimism. But the way that message passing works is that it is actually simply sending a cryptographically signed message saying, or not so much signed as attested, proving that a particular operation happened on Ethereum, or vice versa happened on Optimism. And this is a primitive we can actually work with in order to build a solution for ENS and for other applications that focus on read. So from that, we can sort of go to what would our architecture look like? So the basic idea here is we want to allow contracts like ENS's resolver contracts to request external data. So really anything outside of the scope of the EVM asynchronously. We can use this to fetch storage proofs from a gateway, which is a dedicated server whose job it is to fetch information from a system such as Optimism and format it in a way that's commonly understandable to the client without the client having to care about which particular L2 it is or what the format of the proofs are. And then we can verify them in the callback on the contract and return the result to the client. So a concrete example probably helps here, and here's my ASCII-tastic process diagram for this. We have three relevant entities here. The client is, for example, your wallet or your dapp or whatnot that wants to resolve an ENS name, for instance, or any other task that requires off-chain data. The contract is the smart contract on Ethereum L1 that it was originally trying to query. And the gateway is a service whose job it is to help the client and the contract fetch this off-chain data and return it in a way they can handle it. So the whole system works starting the same way as any regular contract call. So the client makes a call to some function on the contract, which would normally simply return data. But instead of returning return data, the contract reverts with an error. And here we're using Solidity's recent support for custom errors to good effect, because this is a way for us to convey exception data. It's more an exception than an actual error. And the error it returns with has a number of parameters. It says, this is the contract that needs external data, which will usually be the one you just called. Here are the URLs for some gateways that you can consult for this data. Here is the data that you should pass those gateways. So here's the question the contract wants to ask the gateways. And when you're done, please call the callback function on the same contract with the response and also with some extra data. So we get all of this back, all 5 parameters, and the client then goes and makes an HTTP request to the gateway that it was provided the URL for with the address of the contract that requested it and all the call data that contract needed. And it's important to note here that call data, callback function, extra data are all completely opaque to the client. It doesn't have to care how they're formatted, whether they're ABI encoded or something else. The gateway has to understand it in some fashion. The contract has to understand it in some fashion. But from the client's point of view, this is just a blob. So we go and make an HTTP request to the gateway with that data, and it comes back with a result, which again is completely opaque to the client. All we have to know is that it's binary data of some form. And then finally, we call the original contract again. We call the callback function that it told us to call with the data we got back from the gateway and with some extra data that lets it sort of keep context from its original call. And the contract does whatever it needs to do and returns an answer to the client. So in the same fashion as a regular call would have done. And so the upshot of this is that you can use this for any sort of off-chain data fetch. But the case we have particularly in mind is working with L2s and working with proofs. So a concrete example in this case, the client is intending to resolve an ENS name. The contract is an ENS resolver. And we go and ask it, what is the address of this? And it comes back and says, I need some extra data to answer that question. Please consult this gateway. And this gateway is, say, an optimism gateway. And so we go off and we ask the optimism gateway, and it says, here is a blob of data which will prove cryptographically that this name resolves to this result. And when we pass that to the callback function, the original resolver can then go in and it can verify the same set of Merkle proofs and signatures and so forth that a token gateway would, in order to verify that the returned result actually proves that a particular storage slot on a particular L2 had a particular contents, and therefore that this name resolves to this address. So does it solve our problem? Well, we've got no additional trust assumptions because we can build a gateway and a client that verify any sort of proof we want, and we can utilize the existing infrastructure that people have built for message passing and token gateways in order to generate and verify these proofs. There's no L1 commitments on update because we're taking advantage of the system that the existing system for serializing state routes to L1, the very thing that makes rollups work. There's no transactions for queries because we're doing everything via off-chain calls. Clients don't have to know how to query every L2 because, as we saw, every piece of data that the client handles is just an opaque blob to it. It's up to the gateway and the client to agree on the format of that. And there's no hard requirements on the layer 2's capabilities because the client, the contract and the gateway can decide what the format of this is. If you wanted a simple key value store lookup, you could use that using the system. You can format it effectively however you want. And so this pattern, as you've no doubt noticed, is much more useful for much more than just ENS. It's a generic pattern for allowing contracts to make any sort of asynchronous request off-chain. So it works with other external systems. You don't have to be talking to an L2. You could be talking to a flat text file. You could be talking to a traditional API. You can be talking to pretty much anything. The only limitation here is that the contract that made the call has to have some way of verifying the accuracy of the data that's returned. This isn't a magic secret sauce that lets you fetch data trustlessly unless you already have a way to verify that data. So you could use this to fetch the current token price from an API, for instance, but you're still going to need some way to know that the user that's submitting that call gave you an accurate value. But it can be used on any application that needs to read off-chain data. So ENS is the obvious case here. But another example, and one we've actually worked an example for so people can see how it works, and I'll demo shortly, is that you could have, for example, tokens on layer 2 systems. You could have Merkle airdrops where the claim interface is simply transferring the tokens. You don't have to have a specialized site. And really, you can have just about any sort of fetch system you want. And it can be even be used to build bridges, because if you have this proof system, you could use this in order to, say, unlock tokens by moving them back to L1, because you're simply now using this sort of pull model instead of a push model to fetch data. And the best thing about all of this is that it can be abstracted away by Web3 libraries like Ethers and Web3.js. And that means that from a client's point of view, the actual transaction, the actual call just looks like a regular contract call, which I think is probably one of the best things about this whole system. So I have now a very short demo. We have here a sample program, which I'll share now, that this is a fairly standard Web3 application. There's a fair bit of boilerplate here, which I'll ask you to hopefully ignore. What we're doing here is we have a token at some token address. We have a Web3 provider. We have an account we're using to send transactions, and we want to send some tokens from one account to another. And if you ignore these commented outlines, this is a perfectly ordinary application. We get an Ethers provider, create a signer from it, we set up a token contract, and then we just check the balance of the original contract, the original account. We make an ERC20 transfer, and then we check the balance again. So far, so simple. The only change we need to make at the moment in order to support using 3668 to do this is that instead of just the standard provider, we wrap it in this piece of middleware that we've written called the CCIP Read provider. So we take a standard Web3 provider, and this provider here wraps it and provides all of the functionality we just described. And with that, all of the contract calls, so that means the balance of function and also the transfer transaction, suddenly become capable of using 3668 to fetch off-chain data before completing. And so I can demonstrate this end to end. And so here I have a terminal window. I'm going to start up a hard hat node. I am going to deploy some contracts to it, or at least I am if I can remember which command I'm supposed to be running. So please excuse me for 1 second. It is yarn deploy. Of course it's yarn deploy. So now I am deploying the token to my hard hat node. And so in this particular example, our L2 is actually basically a text file of balances that are available offline and are signed by some trusted key. So this isn't using like a real L2. This is a much simpler demo that uses a gateway that basically says, I will sign responses to say they're accurate. And then I will then we'll change to our gateway service and run our gateway. So this is a very simple web server, which I can demonstrate the code for later, that basically fetches data from the text file, signs it with some trusted key, and returns it. And then finally, in the third window, I'm going to actually run the client, and very unglamorously, it simply, here we go, it fetches the balance, it checks the balance of the recipient, transfers one token, checks the new balances. It's not much to look at, but every single one of these calls involved a call to the EIP-3668 gateway and involved transparently fetching and signing data without the client code having to know or care about how that actually worked. And I'll briefly show off the, so these are our contract calls. I'll briefly show off the gateway as well, which is here. And you can see that the whole thing's only about 45 lines long. This is the relevant thing. It implements a function called getSignedBalance. It simply looks up the balances in an array of balances, signs a message attesting that that was the correct balance, and returns both the balance and the signature. So the whole implementation, including boilerplate, is less than 50 lines long. And so finally, what have we done so far and what's next? So EIP-3668 CCIP Read is recently moved to last call. We've done a lot of work on it. We've gone through a number of iterations, and it's gone from a very basic starting point to what I think is the much more flexible and versatile solution we have today. A gateway server library is available. So that is the framework you saw in the last snippet of code I shared. It makes it very easy to write a gateway without having to worry about what the specific HTTP protocol for gateways is. You can basically write handlers that implement effectively Solidity functions is the way it's modeled. An ethers provider is also available. That's in what we were using in the first snippet I shared. And it allows you to make contract calls using CCIP Read without having to change your code at all. And in fact, we anticipate this package becoming obsolete soon because we're working on getting this integrated directly into ethers. So you will simply be able to make these calls without having to make any changes to your code at all. And you can find example code as well as the actual frameworks at GitHub smart contract kit /CCIP Read, which we're developing in conjunction with Chainlink. Next steps, actually getting through the last call stage of 3668, getting it integrated into Ethers, Web3.js and others, and building standardized gateway servers for standard L2s. So we can have a gateway server that, for instance, fetches a particular storage key and returns the key along with its integrity proof. And then that can be used by systems like ENS or anything else without the need to write a new gateway server for every individual application. And that's all I have for the presentation. I hope I haven't rushed through it too quickly.
No, it was nice. Thank you for this nice presentation. The demo, small demo, but it was really helpful to understand. And I hope that the new developers, the new project developers may make use of that. So thank you for that. And yeah, I think I can open the platform for questions now.
Okay, sure. So I had a few questions, if you don't mind. One was that you said that this doesn't make any additional trust assumptions. Don't you end up needing to trust the gateway, though?
No, so the nice, it depends on your application effectively, but you can build trustless gateways. So in the optimism example, the gateway's job would be, for instance, to return a proof of the contents of a particular storage slot on optimism. And what it returns then is the value of that slot and a Merkle proof attesting that that slot is part of a given contract state, and another Merkle proof proving that that contract state is part of the state root. So the contract gets all of that back, and it uses a combination of like Merkle proof libraries and the optimism contracts on L1 to verify that that whole thing is rooted in a valid state root for optimism on L1. So if the gateway lied, then the proofs would fail. The other avenue that a gateway could mislead is by answering one query with a valid answer to a different query. So I ask, what does example.eth resolve to? And it returns me vitalik.eth. And the way we avoid that is by allowing the original contract to pass some extra context to the callback via the client. So there is a second call that never goes via the gateway that allows it to verify that the question being answered is the one it originally asked.
Interesting. I think what I was missing is I didn't realize that you could use the optimism gate, like the optimism contract on layer 1 to verify the state root of a contract. You can verify any optimism contract state root through the optimism contract on. Okay. Yep. Yeah, that's what I was missing from the picture over there. Cool.
And this isn't unique to optimism either, because the fundamental primitive of every L2 is that its security ties back to L1. And the way it does that is by allowing L1 to verify state transitions and so forth. And sort of by necessity, that means we can kind of hijack that behavior in order to get whatever proofs we need without any additional trust.
Interesting. So, and I guess a similar, like the analog by the ZK rollups would also be the kind of ZK commitments. Also, there should be some way to extrapolate a state root of a contract on a ZK rollup from that.
Precisely, yeah. If it's an EVM compatible ZK rollup, then yes. And if it's some other thing, then whatever the equivalent is, that is rooted in the state on L1.
When it comes to things like sidechains, though, then what would we have?
So sidechains are a little trickier. If you, or the same for bridging to other L1s. If you have, if those sidechains have a gateway that allows for signing messages. So you pass in a request and they give you back a message signed by a consortium of validators that says, yes, that's correct. Then we can utilize that same thing. But in some cases, these bridges don't expose that API. They simply expose, token movement, and all of that happens via a private API. And so in that case, we either need to get them to add that public functionality so we can utilize it, in which case there are no additional trust assumptions, but it is still trusted, in the same sense that a regular bridge to that network is. If they won't or can't expose it, then we would have to run our own consortium of signers that attest to the validity of a particular state on that particular network. And that's why, the Chainlink is such an obvious partner to work on this with.
Yeah, that was just clicking for me also when you said that, like a consortium of people agreeing on a particular piece of data. That is Chainlink. Yeah.
And in my book, that's very much of the three possible solutions, that's the least preferable, because it's best to be able to do this first of all with no trust, or second of all with the same trust as you already assumed. But if you need to, you can fall back to the solution as well.
Mm-hmm. So I guess in a similar vein, then, I guess it's easiest for me to phrase this question in terms of ENS, but I guess it would also be an open-ended question for anyone who wants to implement this. How would you vet what gateways get returned from the original exception?
So it's kind of up to the contract. Like if a contract wants to accept insecure data or invalid proofs, then there's nothing we can really do to stop that. There is a potential issue here with things like fingerprinting and so on, where a contract basically just causes the client to make a call so that they then know which clients are visiting that contract. And so for that, we may need some sort of whitelist. But from a security point of view, I kind of view it as the same as the contract could also rely on, on unreliable oracles or none at all, or it could just accept values from the user already. This essentially provides a way to automate fetching data, but it's up to the authors of the contracts to make sure they do it in a secure fashion.
Mm-hmm. Interesting. And also, just by way of clarification, when ethers or a library like that would implement something like this. So I saw in your code that basically you had the standard ERC20 dot transfer with the arguments right after that. So does that mean that basically any contract call in ethers needs to be overloaded, that if it gets an exception in a 3668 format, that it automatically recognizes that as being a part of this EIP and knows to make the additional calls?
Pretty much. It happens at a slightly lower layer than that. It happens at the ETH call RPC layer, because it doesn't need to, because the whole thing's opaque. It doesn't even need to know anything about the ABI encoding the contract call. But it does get intercepted in the way you described. Yeah.
Oh wait, so I think there might be something here that I'm not understanding, right? The way I understood it was that the contract on L1 returns all of this data, and then the front end, like the client, not necessarily a front end, unpacks that data in order to make an HTTP call, and then it makes a separate call after that.
That's right.
So,
yeah.
Oh, okay. So, so what were you saying about it happening on the ETH call layer level then?
Yeah, so the example we gave with the provider there that wraps the standard provider it intercepts ETH calls, and if the off-chain data error is returned, it does the whole dance. But it doesn't need to know the ABI for the call or the return value of the original call, because all the information it needs is provided in that error.
Okay, I get that. Right. That is really super cool. That's it for the questions on my end.
Well, I have a couple of more questions for you. I see this proposal has generated some decent conversation on the discussion to link. And from there, my first question is the compatibility with the IPS. So how important is it to have the compatibility with the IPS-like platform for projects to implement this proposal? is EIP-3668 makes it compatible? If not, what would you suggest as an alternative that can be helpful for project to implement this proposal?
Yeah, so this was an interesting point that was raised quite late in the process, and I'm really glad it was, which is that the original protocol used post messages in a fairly standard RPC protocol. And in doing so, it basically required that the gateway was a dynamic service. But somebody pointed out that, like in many cases, it may be useful to have a static set of proofs. So you could imagine a situation where a contract wants to fetch one of a very large number of pieces of off-chain data, but that data doesn't generally change. So, you know, to take a random example, you might have an NFT where you need to be able to access the metadata on chain, but obviously you can't store it all on chain. And so there you could actually pre-calculate all the possible responses and store them. But that's sort of all for naught if your gateway then has to be a dynamic service and serve them up on the fly, you know, from post requests anyway. So it was pointed out that if we just change the request method to GET and we change a few things around, we can actually support that, and your gateway can actually just be a static web server, and that includes IPFS. And so we just very recently made a few changes to the spec that support that. So it would now be possible to have a gateway that is actually just a directory of files, which I think is a very neat extension to the standard.
That's interesting. I mean, yes, I understand that people are using IPFS, and it will be helpful that if this proposal provides some of the facilitation to integrate that. So that's nice to know. Other thing is about the project implementation. You mentioned that Ethers and Chainlink may have some implementation, or the snippet that you shared. Could you talk about some of the other projects that you can think of that can be simple and useful use cases for this proposal?
Mm-hmm. So I think there's probably a lot of applications we haven't thought of yet, but the ones that immediately come to mind beyond ENS are things like token Merkle drops and airdrops for both the ERC20s and for NFTs, where you could, instead of having to have a dedicated claim interface, you can simply have the token show up, and when the user first transfers it, it goes off and consults the gateway for a proof that they owned it in the first place and uses that in the initial transfer. And the demo I showed, as unglamorous as it is, effectively shows how you can do this. It presents an ERC20 interface, but some of the balances and the transfer functions require off-chain data to complete. And the other example I gave is existing Oracle services. You can rewrite a gateway or an Oracle as sort of this pull mechanism where it requests data when it needs it, rather than a push mechanism where some off-chain service fetches the data and submits it to the contract on an ongoing basis. And potentially this can lead to gas savings where your users update the Oracle when the data is needed, rather than you having to update the Oracle on a regular schedule, even though maybe nobody's consulting it. And as I say, I'm sure that there are others beyond this. You know, effectively, you can think of it as providing contracts with a way to make web requests, which is pretty neat in my book.
Interesting. I mean, talking about airdrops, do you think that with the ENS airdrop that was like announced a few months ago, if this proposal was in place, would have helped?
It's ironic, like, yeah, we're sort of looking at it and we're going, oh, if only we could use the standard we're working on for this thing we're doing, you know, but it just wasn't far enough along. If 3668, if CCIP Read had been integrated into wallets at the time, I think that's probably how we would have done it. And it would have made the UX simpler for users. I guess the other motivation we had is we really wanted to onboard people into the DAO, not just have them claim tokens. And that requires like walking them through what the DAO is and what the constitution is and so on. So in that case, maybe we would have had to just stick with a fairly traditional interface.
Nice. At least now, after the proposal becomes a standard, it would be helpful for the new projects, if any projects decide to do for airdrops in future, might Absolutely. Be useful.
Yeah. So before this EIP, was it possible to, like, or was it not possible to make a network request that was off chain?
I mean, you could implement a similar pattern to what we have here. You know, your initial request can say, hey, go consult this thing and come back with the data, but you'd be building it more or less bespoke for each application. And so you add an awful lot of overhead coding wise to each time you need to do this. Whereas this provides a generic pattern for it, and on the client's end, makes it entirely transparent.
My next question is about the security consideration. The proposal states that the validation required is application specific and cannot be specified on a global basis. So I was wondering, like, in absence of a specified validation specification, do you think there is a room for vulnerability in a project implementing this proposal, maybe failing to properly define information that is required in the extra data argument to allow for verification?
Yes, yeah, I think this is something projects like authors of smart contracts need to understand fully before embarking on, and to take some care with establishing that their what their trust assumptions are and how they're validating them. I think this will be made somewhat easier by having standard gateways for things like optimism and arbitrum and so forth, because those gateways will enforce a particular form of response and reply, and they will come with Solidity libraries that enable a single function call to validate the response, which makes it sort of easier to build the right solution than a shoddy one. But if you're building a custom solution, yes, you have to think first of all about how am I going to validate the response that was returned is accurate, and remembering that you can't trust data sent by a client. And secondly, remembering that you need to be able to validate that it was actually answering the question you asked, not some unrelated question.
That makes total sense. It's important that the developer who are working and implementing this kind of proposal, like interacting with a different chain, it's important that they should look into all the related security considerations. Well, my last question for you is about the advice for dapp devs. Like, would you have any specific recommendation or piece of advice for projects implementing this proposal, like in the sense, like if they have to consider something like very specifically?
I guess most of what I'd advise is covered by my last answer, but I guess I'd follow up by saying we have these existing libraries for writing gateways and for working with the client, but they're still very early. So if you are working on something, we'd very much like to hear from you if these are sufficient, because we've authored them thinking of the use cases we have in mind, but I have no doubt that there will be others that we haven't anticipated. And now is the very best time to improve it and make it more general. And that's already happened several times through development. Like, the standard is substantially better than it would have been if we just released the initial version. And it's not too late to make your voice heard and help improve it further.
Nice. So that's all from my end. And I believe Alita Moore has some more follow-up questions.
Yeah, so I don't fully understand the proposal, and so I want to investigate that more and try to clarify for myself, and maybe that'll be helpful for others. So I am still a little bit confused, like what the exact, because like when I think about an off-chain lookup, I'm thinking about like what comes to mind is that you have like a contract, and then on the contract you're making a network request to somewhere, but then I don't understand, like I'm not really sure where this falls in, because it's like, why would you want to do that in the first place? And then, yeah, I think we'll start there. Why would you want to make a network request in the first place? Like a simple example or something.
Yeah, so I guess the simplest example is you want to save on contract storage because contract storage is expensive. But you still need some of that data in order to complete a call or complete a transaction. So you're storing it off chain, but on chain you're storing something that allows you to verify the validity. So a trivial example is you have a large database of data, you Merkle hash it all, so you construct a Merkle tree, you store the root in the contract, and therefore your callers can provide you with the piece of data needed to satisfy their particular request and a proof that that is part of the tree that you originally committed to. And so all of that's possible today. But when you do it, you'd be building a custom client that runs in the user's web browser that understands how to fetch these Merkle proofs and format them and submit them to the contract. And you'd be writing a custom contract, of course, that understands how to verify those proofs. The difference here with CCIP Read is that you can do all of that, but your client doesn't have to know anything about that. So your client simply makes a call, and transparently behind the scenes, the contract says, please go fetch this Merkle proof for me and return it. And from the client's point of view, it was just a regular call without having to worry about that external data.
Oh, okay, so that makes sense. So it seems like it's like if I'm understanding correctly, this is a standardized solution to like I mean, I want to say like a standardized approach to that problem of like storage being expensive. Does that sound correct?
Yeah, I mean, it's in a sense, like all of it arises from that, because even the existence of L2s is in part because storage is expensive, and transactions.
Sorry to
Who's that?
interrupt. Just a follow-up question. I'm curious to understand, like, do we have any idea of how much gas is being saved? Like, any rough figure?
So it's difficult to say, I guess, because it's very application specific. Like, and we have two basic operations you can do here. You can make contract calls, and those have always been off-chain with no gas. But the difference is that now you can easily facilitate fetching data from a gateway as part of that call. And if you decided to store that all on chain because you didn't have a practical pattern for that, then it could be effectively unlimited. And then you have transactions where again you can now fetch it off chain instead of storing it on chain. And so in that case, in some cases, what you're doing is you're pushing the gas from the time when you're deploying the contract and inserting the data to the time when you're claiming it. And if you don't expect, if you don't expect all of the data to be interacted with on chain in a short period, then it may be much more gas efficient to do that and only do it as it's on demand. Even in cases where you expect most of the data to be interacted with, it may still be cheaper though, because call data is an awful lot cheaper than contract storage, which is the foundation of roll-ups basically. So even in a case where you have a data set and you expect 100% of it to be needed, being able to just store a hash and being able to submit it on demand and call data may be a big benefit. So I don't have concrete numbers for you, unfortunately.
That's all right. I was just wondering, like, if we can get a good estimate of that. Thank you.
Can you explain more to me what the gateway is? Like, is that a standard interface that's used throughout the industry?
So we started off by using JSON RPC, same as used by Ethereum nodes. And, that was our initial solution. But in order to support static gateways like IPFS, we've transitioned to a simple GET request. So it's standard in the sense that it's HTTP and JSON. Basically, the gateway, the client makes a request to the gateway with the sender address and the call data in the URL. And then the gateway responds with a JSON message containing the response data. So it's an extremely simple RPC format.
Okay, that makes sense. And then I'm assuming that if a client or wherever this external destination would kind of interface with that format, and that's the idea?
Yes, yeah. So the client understands the basic RPC protocol, but the call data and the return data are just opaque binary blobs to it. It's up to the contract to form and interpret those.
Are there any other applications that you know of, like right now, that are maybe building off of the CCIP Read, or maybe the old, like, more bulky solution?
So since I since it went final, I've had a couple of people reach out and set up meetings and so on because they have ideas that they think will fit well with this. But beyond the ones I already described, like airdrops and off-chain data of that sort, I'm not aware of other applications for it that are being actively built out today.
Well, if anyone else has any question for today. I think presentation itself was quite helpful and it explained a lot. I don't know if we have, in production, any project implementing this, but we may hope to have someone soon in near future. We appreciate you, Nick, taking out time to talk about this unique proposal, which I think will be used in many more upcoming projects for off-chain data retrieval. So thank you, and thanks to all our cat herders and other participants. For people who are watching this recording, the current status of the proposal is last call, which is ending on January 24th. It means the EIP is almost ready and soon going to be in the final status. So if you have got any concerns, this is the best time to join the discussion to link and share your concerns. In case of no significant changes requested during this review period, I hope this proposal move to the final status by the end of this month. On this note, thanks to all our YouTube viewers for watching this episode. If you like this episode, hit the like button, share it with the people, because we want that all these proposals that we are discussing in this series